Very good afternoon to one and all. What I discussed in the last class regarding non-linear pharmacokinetics, right? So, in this non-linear pharmacokinetics, what the meaning exactly? Few drugs or some drugs will not follow the linear kinetics. Then, how the linear relationship between the time and concentration? It will be a linear. But in case of non-linear pharmacokinetics, the drugs will follow mixed order, mixed order, that is either of zero or first or both mechanisms, both drug release mechanisms at the same time, at the same time or at different time intervals, different time intervals. Or this nonlinear pharmacokinetics are also called as capacity limited. These capacity limited kinetics we have observed in metabolism pathway, metabolism of drug pathways. So some organs or few organs will be limited to its capacity to do its metabolism. So that's why these are called as capacity limited drugs. So your nonlinear pharmacokinetics, the drugs which will follow these types of kinetics are also called as mixed order kinetics, capacity limited kinetics, and one more important thing, dose dependent kinetics. These drugs will travels in your body with the depending upon the drug dose in your body. So how much you need to take the dose of the drug, that is also very important to exhibit either linear or non-linear. So these are the synonyms for your non-linear pharmacokinetics. Until now we have seen some saturation mechanisms of few drugs. Few drugs will get saturated either of absorption phenomena or with distribution phenomena or with metabolism or with excretion. So few drugs will be saturated with either of these mechanisms. That's why they may undergo non-linear pharmacokinetics. They may exhibit non-linear pharmacokinetics because of the saturation of either of these mechanisms. So till now we learned up to this point. So next one is the most important thing, that is one equation is there to explain the nonlinear pharmacokinetics by mathematically. The scientist who derived this equation is Michaelis Menten equation. So in this class I am going to explain you about this Michaelis Menten equation. Before that you have to learn some points. Okay, I got these points in other textbook, okay, other than this Brahmanka textbook. So you have to read these two curves also. When you plot the graph between plasma drug level versus the time, it will give three different curves. See here, A, B, C. So this B curve is indicated with the small dose of the drug. So when you take the drug dose with the small quantity, it will give first order kinetics. That means in the sense of a straight line. So when you take, so here there is no saturation will be occurs. Here when you will get the straight line like this, there is indication of no saturation. And at times and at the point C, it will be based on the curve B. So it will be dependent upon the dose, that is twice to B curve. Suppose in case if you take 10 mg of the drug for B curve, then it will be double for obtaining the C curve, that is in the sense of 20 mg. So when you take the drug to draw a kinetics between the time versus plasma drug concentration level, if it yields a straight line, as I am showing the point B, it is a straight line. In this case, the drugs will take small dose of the drug, then it will follows first order kinetics and it will give the straight line. Because of the no saturation, the drug will have the drug will give no saturation, so the drug will give straight line with the small dose of the drug. And then this dotted line C will indicates the dose which you take. In case of B curve, it will be double. So the dose will be twice, that is double. Okay, it will be equal to the dose of A curve. So here in case of A curve, you are going to take some highest amount of the drug. As compared with B curve, A curve will give you when you take the highest amount of the drug. At some point, it will get saturated. Your plasma drug concentration versus time curve gets saturated at the highest amount of the drug. Later on, it will be decreased. The plasma drug concentration will be decreased. So, it will give you the A curve. So, this is the A, B, C. These three curves will indicated you. It will be dependent upon the dose. The nonlinear pharmacokinetics will be dependent upon the dose. So, how the variation of the graphs we are going to observe here on the basis of the dose. Plasma level time curve for a drug which exhibits saturable kinetics. When a large dose is given by IV bolus, initially the elimination of the drug is slow. As in case of A, I am talking as in case of A. Initially, when you given the drug by IV bolus, there is an elimination of drug will occur slowly and it becomes rapid at low plasma drug concentration level. What is the exact meaning of this sentence? See here how the A graph will be. Up to some extent it will give a steady state, then it will be decreased. Your plasma drug concentration is decreasing. So what it means? The elimination of the drug is slow at high concentration of the drug. After that, the elimination will be increased with decreasing the plasma drug concentration. So that is what the meaning. The elimination of the drug is slow and it becomes rapid, or it is increased or rapid at the low plasma drug concentration level. That's what the graph is declining here. Here you have low plasma drug concentration levels, right? So this is the meaning for this. And when you take the differences of the drugs, either there may be a small dose or there may be a highest dose of the drug. So there is a variation in the graphs. The drugs will be exhibited in these three variations in the graphs. So this is the explanation for this plot. And then in order to determine, so here in the previous slide, you are going to determine the dose dependent kinetics. But here you are going to determine various doses, the plasma drug concentration curve obtained for each dose. In the previous graph, you are going to determine only small and high doses. That's it. So in these graphs, you are going to determine various doses, either 10, 20, 30, etc. Various doses. How you are going to determine? The curve should exhibit parallel slopes if the drug will follows a dose independent kinetics. Alternatively, area under the plasma level time curve at various doses should be linear. What is the meaning for this? If the dose of the two drugs or if the dose of the three drugs will be following dose independent kinetics, that means these are not depending upon their dose. So in that case, the curve should be parallel. The curve should be parallel at dose independent kinetics. The drug will not following the dose dependent. Here the dose independent kinetics it will be following. Then the curves, these two curves will be parallel slopes, parallel to each other. As in case of areas under the plasma level time curves, at various doses, either 10, 20, 30, etc., various doses, it should be linear. See here, when you take the relationship between the time and AUC, area under the curve. Here not the plasma drug concentration, remember it. When you take the time versus area under the curve relationship, you will get a straight line of Y. Y is the dose independent drug. Here it is a dose independent drug. So this Y is nothing but the drug. This green color line will says you about it is following the dose independent kinetics. That means it is not following your non-linear kinetics. Okay. Then this pink line, this curved pink line, that is one more drug. Here it is following saturable elimination or dose dependent. It is following non-linear pharmacokinetics. This X drug is following non-linear pharmacokinetics and this Y drug is following linear pharmacokinetics. Linear pharmacokinetics are also called as dose-independent kinetics, and dose-dependent kinetics are also called as non-linear kinetics, right? Here, what is going to happening here in case of non-linear kinetics? There is a saturable elimination process is happening. That's why you are getting a curved line. So this is the major relationship between the time versus AUC. Okay, and this is the plasma drug level versus time relationship. These two are coming under non-linear pharmacokinetics, introduction of ADME saturation processes. So causes of non-linearity you have to write up to this mark. And the next part in your syllabus is Michaelis Menten enzyme kinetics. So this is the most important question as in case of your final examination. Michaelis Menten enzyme kinetics. Saturable enzymatic elimination processes. You may call it as these two types. Saturable enzymatic elimination processes. So it is also called as capacity limited metabolism or mixed order kinetics. So you can express the enzymatic elimination can be following equation. See here in this equation, it is going to explain you the kinetics will follows basis on enzyme. See here E plus D. E means what? Enzyme. D means drug. So when this enzyme is attached or added to the drug, it is forms a complex like enzyme drug complex. The formation of this complex is reversible. Reversible. See, the arrow marks are indicating you both sides. If it is indicating this both sides, it is denoted you as the process is a reversible process. Don't get confused with reversible and irreversible. Okay, so this process is reversible. Which process? When your enzyme is added to drug, it will follows enzyme drug complex, or enzyme drug complex will yields separate enzyme with along with the drug. So this process will be happening between the rate constants, of K1 and K2, because the process is involving in two ways. So the first way you have K1 as a constant. In the second case, you will get K2 as a constant, because here involving two processes. Those are reversible processes. That's why we are going to get two rate constants, K1 and K2. And the next case, this enzyme along with the drug complex, it yields plus enzyme plus other product. This P is nothing but the product. So this process involves the rate constant of K3. So here it is not a reversible process. It is an irreversible process. That's why we will get only one constant. That is nothing but K3. Here two constants K1 and K2. So this is the general enzymatic elimination process. This is the general enzymatic elimination process. Enzymes usually react with the substrate. This is of substrate, drug substrate, to form enzyme substrate complex. Enzyme substrate, nothing but enzyme drug complex. Then upon this K3 constant, it yields an enzyme separately and the product separately. The enzyme can go back to react with another substrate to form another molecular product. Many elimination processes. First, everyone has to know the how many types of elimination processes you have. I think you might have studied under excretion topic. You have active secretion, active reabsorption, and the drug metabolism. These three of elimination processes: active secretion of the drugs, active reabsorption of the drugs, and the drug metabolism. By the use of these three processes, your enzymes will be involved to perform particular process. See, either it may be a metabolism or it may be a excretion, but those will comes under elimination, right? So that's why many of the elimination processes, either of these three, will involve enzymes. At high concentrations of substrate, limited number of enzyme molecules involved. So, if you take the high concentration of the substrate in the sense drug. So, here there is a limited number of enzymes will be involved to get a saturation. Why we need to get a saturation? We need to follow here non-linear kinetics. For that reason, we are going to get a saturation. So, where you will get this saturation? At high drug substrate levels, nothing but high drug concentration levels. So, how the equation will be? This is a very important equation. Once again, I am telling you, just learn, listen carefully. Michaelis Menten equation. With the help of this equation, you are going to explain the capacity limited or saturable processes. The kinetics of capacity limited or saturable processes is best described by Michaelis-Menten equation. So, what is the equation? Minus dC by dt is equals Vmax into C. Vmax into C divided by Km plus C. This is the basic equation for this Michaelis-Menten. Everyone has to remember this equation, entire this sixth unit. dC by dt is equals Vmax into C divided by Km plus C. This is of equation number 1, where dC by dt is the rate of decline of drug concentration with the time. What is this rate of decline? Generally, dC by dt is rate of drug concentration. Here you are indicating minus also. Minus is indicating you decreasing or declining. So here the rate of drug concentration is declining with respect to the time. See here how the graph will be. This is the time, this is the concentration. No? So here the rate of drug concentration is declining with respect to the time. So that's why minus of dC by dt is equals rate of decline of drug concentration with time. And what do you mean by Vmax? Max means maximum, highest level. So instead of using highest word, you can use it maximum. That is the exact suitable word. This is the theoretical maximum of the rate process. So how much the drug will process its rate, the maximum theoretical rate process of the drug, that is of Vmax. And Km is the Michaelis-Menten constant. So here you need to remember Vmax and Km. Vmax is the theoretical maximum of rate process and Km is the Michaelis-Menten constant. There are three situations you can consider depending upon the values of Km and C. First, everyone has to write this equation. This is of the Michaelis-Menten equation, which will explains you the kinetics of saturable process of drugs. So here we are going to concentrate Vmax and Km. Km is Michaelis-Menten constant. Vmax is theoretical maximum rate of the process. So here you have three different situations are there. These three situations will be dependent upon the values of Michaelis-Menten and the C value. C is the plasma drug concentration. So whenever they will ask to write this Michaelis-Menten equation, including these three situations, you can write it. So, what are the three situations? When first situation is when Km is equals to C. What it is? What it is saying us? Km is the Michaelis-Menten constant when it is equal to the plasma drug concentration. When it is equal to the plasma drug concentration. How the equation will be? See here in the textbook directly they have given like this. So you have to derive minus dc by dt is our basic equation, right? So this is equals V max into C divided by Km plus C. This is our basic Michaelis-Menten equation. So in the first case, it is describing you Km is equals to C. Michaelis-Menten constant is equals to plasma drug concentration. So how the expression of this equation 1? It will becomes V max into C divided by Km is equals to C. So you can write C plus C here. V max into C divided by 2C, right? C plus T is 2C. So here 1C will get cancelled and here C will get cancelled. That is equals V max by 2. So in the first case, Km is equals to C, your V maximum, theoretical maximum of the rate process. This is a very important. Theoretical maximum of the rate process will becomes half. So in your textbooks, they given first this equation, then this one, then this one. So if anyone wants to know the derivation, you can write it. When Km is equals to T, we will get V max by 2, right? So this is the theoretical maximum of the rate process. The rate process is equal to half its maximum rate. So the rate process represented in the plot of dc by dt versus C. How the process will be. Okay, these three graphs I will show you at a time. So the next case, first case is Km is equals to C. In the next case, what it is? Km is greater than C. If a drug is at low concentration, if a drug at low concentration, it will undergoes a saturable biotransformation. Then Km is greater than C. That means what? Your Michaelis-Menten constant is more than that of concentration available for your drug. So, why? Because your drug is at low concentration. At low concentration only it is attaining a saturable biotransformation. Then here the Michaelis-Menten constant is more. So that your concentration of drug is neglected here or negotiable. So then you will get dc by dt is equals to V max into C by Km. See, what is our equation? dc by dt is equals to V max into C by Km plus C. So here Michaelis-Menten constant is greater than C. At low drug concentration, the drug metabolism will undergo saturable kinetics. So the equation will becomes, here you are going to neglect the C. So Km plus C. This whole term you can neglect here. dC by dt is equals V max into C by K. Sorry, C is 0 here. So Km plus 0 is Km. So that V max into C by K. This is the final equation when the state of Km is greater than C. Is it right or not? C. V max into C by Km. C. V max into C by Km. Sorry, Km. Okay, so this is what our second situation, that is of Km is greater than C. So the Michaelis Menten constant is having more. When the low drug concentration is producing some saturable biotransformation kinetics, there a state we can neglect the plasma drug concentration. So C is become 0. So Km plus 0 is Km. That's why your equation is like this. This is the case Km is greater than C. Then the third case Km is less than C. See, if Km is less than C, what is the equation? dC by dt is equals V max into C by Km plus C. So, dC by dt is equals to V max. Under this condition, Km plus C is equals to C. This Km plus C is equals to C. Because here Km is less than C. That means Michaelis Menten constant is having less with that of plasma drug concentration level. So here it is highest. So that you can consider this Km plus C is equals to C, because here you are going to neglect this Km because it is producing some low concentration as that of this plasma drug concentration original. So this Km plus C is become C. So V max into C divided by C. C will get cancelled. So that you will get V maximum. When the level of Km is less than C, you will get dC by dt is equals to V maximum. Maximum theoretical rate process. So when there is a less Km is less than C, you can neglect Km here. When Km is greater than C, you can neglect C here. So then you will get these three kinds of situations. Three kinds of situation can be depending upon the values of Km and C. First one is Km is equals to C, and the second one is Km is greater than C, and the third one is Km is less than C. Here you have three different equations. So this is of, there are three situations. Okay, first one is V max by 2. Here Km is equals to C. Where you will get this V max? Km is greater than C. Sorry, less than C. And then Km is Michaelis Menten constant. So how the relationship of these three situations by explaining this Michaelis Menten equation. This is the relationship between the elimination rate dC by dt and the concentration of the drug. See here, when you plot the graph between these two, dC by dt and C, you will get a curvilinear plot. So up to this mark, where you will attaining this first order kinetics at low doses. This is the most important point. So up to this mark, the drug is traveling very linearly. After that, it is going some curved line. So here it is exhibiting mixed order kinetics. That means 0 and first order it is going to expressing here. After that, at high doses, the drug will follow a steady state elimination process. This is zero order rate elimination process at the high doses. So here, this is termed as V max. This is the maximum theoretical value for the rate process. So here in this graph is explaining you about how the drug will follows first order, zero order and mixed order. First order will follow at low dose, zero order will follow at high dose. And the intermediate doses, you will get a mixed order kinetics at this point. So here, how you will observe this all three orders in one graph? By the variation in the curve structure. See, it is not like this, or else it is not completely like this. So it will be like this. Up to some extent, it will follows first order at the low doses. At increasing the dose, that means at intermediate dose, it will follow mixed order. At highest doses, it will follow zero order. So we will able to see these three order of relationship of your drug at one graph. That is explained by Michaelis Menten equation. These three are the different situations, right? So this is about the Michaelis Menten equation, and in that one more part is there, that is estimation of Vmax and Km. So here you have to remember these two terms are very important. Michaelis Menten constant, maximum theoretical rate process. So you have to estimate, you have to calculate these two parameters. Okay, how you will calculate? I will tell you. The parameters of capacity limited processes like metabolism, secretion, excretion can be defined by assuming one compartmental kinetics. What do you mean by one compartmental kinetics? In case of one compartmental kinetics, you have to assume our total body assumed as a single uniform compartment, right? Single uniform compartment. Total body, there is no separations for the drug, and that elimination involves a single capacity limited process. So you can estimate this Vmax and Km by assuming the one compartmental kinetics. In case of one compartmental kinetics, you can assume our total body unit as a single uniform compartment. So here the elimination is also involving only a single capacity limited process. Then you can able to estimate this Vmax and Km. So the parameters Km and Vmax can be assessed from the plasma time data collection after IV bolus administration. See ma, if you give an IV bolus route, if you give a drug through IV bolus route, this drug will follows non-linear. Definitely it will follows non-linear. Then only you can able to find out the Km and Vmax. So the non-linear pharmacokinetic drug will be given by IV bolus. You can assume as one compartmental open model kinetics. Then you can able to find out Km and Vmax. Okay. So in your textbooks, first they have given this sentence, then directly they have given this equation. From this equation, so here you need to learn the derivation, how you will get the equation, this equation from this equation. So Seema, here this is our basic Michaelis Menten equation. So finally you will get the logarithmic form of this equation. I will derive for you. Okay. So derivation from equation 1 to equation 2. So first everyone has to write this equation 1. Then what is the equation 1? dC by dt is equals V max into C by Km plus C minus dt, right? So you can split the equation. You can split the equation like this. Then dC by dt is equals C by Km. C by Km. Then minus Vmax by Km. Then Vmax by Km. This is of second equation. Then your C will become C0 minus C. Why you have to write C0 minus C instead of writing C? See, ma'am, when you take the plasma drug concentration versus time curves, you have to calculate the initial plasma drug concentration also. Then only you can able to find out the difference between initial plasma drug concentration and the later on the plasma drug concentration levels. So C0 is the initial plasma drug concentration at time 0. C is the plasma drug concentration at time t. So for that reason, in this equation, instead of taking C, you can take it as C0 minus C. Then your equation 2 will becomes, write down, dC by dt is equals C0 minus C divided by Km minus Vmax by Km. So this is the plasma drug concentration difference, that is at time 0, that is at time t. You will get the equation like this. Then you have to do integration for this equation. So write down how the integration will be. 0 to t dc is equals to integration from 0 to t. You can write C0 minus C by Km minus Vmax by Km into dt. See, when you integrate this equation, integration from 0 to t, dc is equals to 0 to t integration within the brackets C0 minus C by Km, Vmax by Km into dt. Here we have a dt, right? So then you can do logarithmic form for this above equation, log form of the equation. Then you will get log C is equals to log C0 plus C0 minus C by e to the power of minus Km. See ma, when you do logarithmic form, when you apply log form to the above equation, log C, here integration 0 to t dc is log C is equals log C0 plus C0 minus C by e to the power of minus Km. When you convert some logarithmic form, same as that of your first order derivation. So you will get e to the power of minus Km minus Vmax by e to the power of minus Km. Okay, here Vmax into t. After removing this integration 0 to t dt, you will get a t here. So this is of C0 minus C by e to the power of minus Km minus Vmax into t by e to the power of minus Km. Then you will get log C is equals log C naught plus C0 minus C divided by 2.303 km. By removing this mono exponential form, you will get a value of 2.303. That's why it is a 2.303 km minus Vmax into T divided by 2.303 km. This is the final equation where your textbooks will be given. See, log C is equals C0 plus C0 minus C by 2.303 km minus of Vmax into T 2.303 303, not 0 here, 2.303 km. The same equation we will get here. This is the derivation of equation 1 to equation 2. Okay. So this is what the parameters of Km and Vmax can be assessed from the plasma drug concentration when you have given the nonlinear pharmacokinetic drug through the IV bolus administration. When you assumed it as it will follows one compartment open model. You need to focus in Michaelis Menten 3 situations. And one more thing, you have to learn the derivation. This derivation. Estimation of Vmax and Km. You have to learn the derivation from 1 to 2 equations. This is about today's